Hey data junkies, welcome back. INST314 Statistics for Information Science with moi, Sean Jansen, your facilitator and guide through the wonderful wilds of data analysis and quantitative research that we're looking at. We're continuing our journey into Inference Part 2, the Introduction to Hypotheses, Power, and Effect Size, in the second of the three video series. This one is looking at alpha, p-values, and hypothesis errors. Again, we were looking before at the null and alternative hypotheses, and this one we're going to be more so looking at familiarizing ourselves with alpha and p-values, which is one of the fundamental tools in our toolkit to help us determine if we are going to be able to reject the null hypothesis or not. So, revisiting the three big questions of statistics, we're always concerned with how big is it, what difference does it make, and are we sure it's just not dumb luck? Remember the last one, because in alpha and p-values, as we get started, we're going to revisit this idea of are we sure it's just not dumb luck? What does that mean? That means that we could be out here collecting samples and doing analysis, and just by random chance and trivial association, the data that we have is not truly representative of the population, and so no matter what it is we find, it's just not going to connect back. And that's just dumb luck on our end. The same is true if, well, I'll save that for when we get to the type 1 and type 2 errors here. I won't get ahead of myself. Significance level is a defined level of risk. This is just talking about risky behaviors and how much you're willing to put your cards onto the table before it is you're going to fold with your hand. Some of you are the type that you might wait to study and complete your assignments until the day before the exam or the day before the assignments are due, and you're taking on an amount of risk that you're going to understand the materials enough that you're going to be able to finish it on time and without problems and without errors by the time you get there. These are all different levels of risk. Some of you who are less risk averse will start your materials sooner so you don't run into those sorts of little troubles and you can have time to build yourself out. It's not saying that okay. I have my opinions on which of these methods is better, but most of you are going to do as it is that you need to do, and it's the decisions you're going to be making is partly on how much risk are you willing to take. That is a core concept to what we're talking about here with hypotheses and these reasons here. So significance level is talking about the probability your results could not have occurred by chance alone. This is that amount of risk you're willing to take. What is the chance that I'm willing to take, the maximum level of risk, that what I find could just be by that dumb luck coincidence, and I really can't use the results from there. That is the idea of statistical significance. Well, significance, and in this case, we are going to have two kinds, statistical and substantive. I was just really referencing before the statistical component. How much risk are you willing to take before you can reject the null hypothesis when it's actually true? Remember and recall that we're always starting out with the assumption that the null hypothesis is true and we are trying to disprove it, make it falsifiable. And so this is going to help us to determine, are we possibly true or not? The other sign of significance is substantive significance, and that is where we're talking a bit more about a qualitative component on the amount or the size of the difference in the effect. This is our so what answer, the who cares sort of answer. So getting back to the statistical side as we dig into this, let's talk about alpha. Alpha is a number. It's a value you set as the threshold. It's the maximum amount of risk that you're willing to take. We speak about it in terms of proportions or percentages. And this is also our benchmark, not only for the maximum level of risk, but it also serves as that barrier, that obstacle that we were saying is you need to be able to cross this threshold in order to say you have strong enough evidence to go ahead and reject the null hypothesis. The smaller your amount, the smaller your level of statistical significance, the more evidence you need to reject the null. So if I was to go ahead and say that the alpha is a probability that we're going to reject it, given the fact that there is no effect, then we could use something like an alpha of 0.05 or 5%. Remember, it can be expressed as a probability, 0.05, or as a percentage, 5%. And that's what we're saying is, this is the risk I'm willing to take when we see an effect that doesn't actually exist. So 5% of the time, I could have an amount that is not necessarily accurate. It's just by dumb luck and trivial chance that I got this sort of result here. The same thing can be said in terms of 0.05. It's a 0.05 probability that I have the results that I have just by dumb luck and chance. And I said before, the lower the alpha, the more evidence you need. So if I only want to have less risk, maybe a 1% alpha, then I'm going to need stronger evidence to make sure that I'm meeting that level of risk. Conversely, as alpha goes higher, maybe 10%, then I'm willing to take on a bit more risk to see that I might be wrong based on what I'm finding here. One of the important things to keep in mind here is that you always set your alpha when the study begins. Don't set it afterwards. We're going to come back to that. The other half of this coin is the p-value. P-value is short for probability value, and we match this against alpha. The p-value, its technical definition, is the probability that you would obtain an effect observed in your sample, or larger, if the null hypothesis is correct. Remember, if the null hypothesis is correct. So in simpler terms, the p-value is going to tell you how strongly your sample data contradicts the null. You start off saying the null is true, you're going to go ahead and get some effect, you're going to get a probability that says this is the probability of getting the effect that I found, and it has some strength. The smaller the p-value, the smaller the probability you're going to find this if the null is true. And if that's the case, then the smaller the p-value, the stronger your evidence against the null. So then what we're looking at is you can take that p-value and compare it back to the alpha to determine if you're going to be statistically significant. Now keep in mind that p-values are not the likelihood of rejecting the null that is actually true. That's what we call type 1 error. We're going to get back to that. P-values are also not the probability of making a mistake. It's not a 5% chance that I'm wrong. You're going to get numbers, and those numbers are going to be what it is. They are going to be the data from that sample. It's not to say that you would be wrong going back to the population. It's just that the sample that you had was not representative as true. So keep in mind, it's not the probability of making a mistake. It's just the probability of finding differences from the null. Now, the analogy that I tell everybody as we're comparing p-value and alpha, because you have to bring these two together, is the concept of driving and speeding. Most of you, I'm assuming, have driven a car or know someone who has, and are potentially familiar enough with the idea that roads have speed limits. And you are, in theory, not in theory, in practice, you are not supposed to go faster than the speed limit while you're driving. Otherwise, you get in trouble with the police and can get a speeding ticket. So we can take this analogy and frame this using alpha and p-value. Think of alpha as your speed limit. It's set. When you're driving down the road, the speed limit is set, and that is what it is. It doesn't vary. Oh, yes, we can go down the rabbit hole and say speed limits can vary as you go down the street. But in our example right here, we're just having a constant speed value. And so you set the speed value, the speed limit, while you're driving, and that's your alpha. How fast are you willing to go before you get in trouble with the stats police? And then the p-value is how fast are you driving? That's that probability of getting your result. And if your p-value is less than your alpha, then you are safe. You are going at or under the speed limit of alpha. Now, if your p-value exceeds alpha, you are going faster than the speed limit, then you could get in trouble with the stats police. Now, this isn't trying to say that having a high p-value is bad. I mean, we can take that as it is. But what it's really saying is that you are not able to reject the null hypothesis. We fail to reject the null hypothesis when your p-value is larger than your alpha. When your p-value is equal to or smaller, then we are statistically significant and we reject the null hypothesis. So again, keeping in mind the analogy of the speed limits. Alpha is the speed limit, p-value is how fast you're going. Keep that in mind and you'll never get it wrong. Now let's talk a little bit about testing error. Right? We're trying to say that we're going to get a p-value and we're going to have an alpha and we're going to reject or fail to reject. But are we always going to be right? And when we're talking about errors then, we've got these two types, type 1 and type 2. The difference between them is fairly straightforward, but we're going to give you some examples that you can work with here. Type 1 errors are what we call alpha errors. They're also known as false positive errors. They're called false positive because we found something in the data that says, yes, this is different than these nulls, but in reality, the differences we find don't truly exist at the population level when we infer upward. Type 2 errors are the converse of this. In this case, there is a real difference out there, but the data that we had failed to detect these particular differences, and so they're called false negative errors or beta errors. When we put this into a little bit of a table, it might become a little more clear for you. In the rows, we have these decisions. What is it that we decided based on the data that we have? And then in the columns, we have the reality. What is the actual situation at the population? So when we have overlaps between decision and reality that are congruent, such as we failed to reject the null hypothesis, and in reality the null hypothesis was true, then we have a correct decision, and everything's fantastic. Likewise, when we reject the null in favor of the alternative, and the null hypothesis really is false, meaning there is a difference out there, again, you've made a correct decision, everything is fantastic, everything is awesome. The trouble then happens when we have a disconnect between these two. When you reject the null hypothesis in favor of the alternative, and in reality, the null is true, that there is no difference, then you've committed a type 1 error, that false positive error. You found something that really doesn't exist, just by luck of the data that you find these things. Also, if you fail to reject the null, you did not find a difference, when in reality the null was false. There is a difference. Then you've gone and committed what we call a type 2 error, also known as the false negative error. Now, how do I remember which one is which? Because this can get kind of confusing. Type 1, type 2, false positive, false negative. So there's a couple statements that can help you out. And we're going to do these in terms of negative statements. Type 1, we can use the statement, I falsely think the hypothesis is true. 1, false. Type 2 can say, I falsely think the hypothesis is false. 2 falses, right? So in type 1, I was wrong to think the hypothesis is true. And the second one, I falsely think the hypothesis is false. 2 falses. Help keep them apart. We can also use a little story here. There's the idea of the boy who cried wolf. For those of you who haven't figured this out, there's the little boy, and he's out tending the sheep, and he gets bored, so he goes ahead and says, wolf, wolf, and there's no wolf, he just wants attention. But all the villagers come out, and they believe him. They said, there's a wolf, let's get the wolf. But what's actually happened was they've committed a type 1 error. The boy says, hey, I found something, when there wasn't anything there. Type 1 error. And he goes out and he does this a few times, the villagers get kind of ticked off. So when there actually is a wolf that comes along, and the boy cries wolf to get help, nobody believes him, nobody comes out, bad things happen. That's the type 2 error. That there was an issue, nobody came out in support, nobody found it, and therefore we've committed that type 2 error. So what happens when we put this into sort of statistical practice? Let's look at this little snapshot here from XKCD, which, if you haven't read, is an amazing online comic strip. I highly recommend it. And keep in mind that we're talking about we can go out and get these samples, right? As I go out and I collect my data, and I'm going to get a p-value, and I have my alpha, every time I go out and get a sample, I'm going to get a different p-value. And so in the XKCD comic here, what they were looking at was jelly beans being linked to acne, and they go out and they do a test, not significant. Go out and do a test, not significant. Go out and do a test, not significant. And they do it again and again and again, and eventually they go ahead and boom, one of them says, aha, jelly beans do cause acne. We have a p-value of less than alpha 0.05. It is statistically significant. This must be true. Be careful of things like that. Don't be that person. This is the idea that if you go out and dig enough, you are going to find something. If by no other reason than dumb luck. What they're finding here, if they're testing it again and again and again and again, and they find that one that says, aha, here's a relationship. In this case, it's probably a testing error, because all of these other tests and all of these other samples, they had a different conclusion. So let's be cognizant of that if you're in the sort of situation that you're testing multiple times. So with that, I'd like to close this video with this concept and idea of p-hacking. I said before that we set our alpha in advance, we use statements that are specific, from the previous video when we're talking about these good hypotheses. And so p-hacking is a fracking for statistical significance. We just sort of were playing fast and loose with our alphas and our hypothesis statements so that when we go ahead and find something that favors us and makes our stories look good and helps us get attention, when in reality we could be committing statistical sins and reporting things that aren't actually there. Don't be that person. Don't go to the dark side. I don't care if they have cookies. Don't do it. And with that, I'll see you all in the next video.